You might find yourself wondering, as I often do, what's the next big leap forward in artificial intelligence?
It's definitely a hot topic.
Well, today we're diving straight into something pretty fascinating. Welcome to Technically You, where we decode the most game-changing tech in the digital world. Today we're covering neuromorphic computing.
Awesome.
Yeah, think of it as trying to build computers that actually operate more like our brains.
Exactly. And for this podcast, our goal is pretty clear. Let's really try and grasp this whole brain and split approach to computing.
Okay,
We've pulled together the key info to explore what it really is and maybe more importantly, why it holds such significant potential for you, the listener.
now let's get right into it then. What precisely is neuromorphic computing in simple terms?
Well, in essence, neuromorphic computing is a design philosophy really for computer hardware.
Okay.
And it draws direct inspiration from how the human brain is structured. So instead of the usual artificial neural networks or ANNs, which most AI uses now, it focuses on what are called spiking neural networks, SNNs for short.
Spiking neural networks. Okay, that sounds a bit technical. Can you break that down a bit more?
Sure, think about it like this. Conventional AI often processes information in a sort of continuous stream.
Right.
But our brains and SNNs try to copy this. They work more on the principle of neurons firing only when they get a specific trigger.
Ah, so they spike.
Exactly, those firings are the spikes. And this whole event-driven way of doing things, it leads to remarkably efficient processing.
Efficient processing. Okay, that definitely grabs your attention. So, what are some of the main characteristics that really set neuromorphic computing apart?
Well, there's several key things. First, as we kind of touched on, is that event-driven processing.
Right?
Unlike your typical CPU in a computer, which is, always chugging away and always on, neuromorphic chips only wake up and process information when there's an actual event, a signal that tells them to activate.
Okay, so they're not wasting power just sitting there.
Precisely. It eliminates a huge amount of wasted processing power. You could maybe think of it like a security guard who only really pays attention when they hear a noise or
See movement instead of constantly scanning an empty room.
yeah, that's the basic idea. Very resourceful.
That sounds incredibly efficient. Like a sensor that only sends a signal when something actually happens.
Exactly right. And that connects directly to the second key feature, low power consumption,
Ah, because they're not always on.
and not always running full tilt. They use considerably less energy than traditional systems.
Okay.
And this makes them really appealing for things like Internet of Things devices, IoT, and edge computing anywhere.
That makes perfect sense. For a tiny sensor out somewhere running on a small battery. What else makes these brain inspired chips stand out?
Parallelism, that's another really vital aspect. So just like our brains can juggle loads of different tasks at the same time, right?
Yes, thinking, seeing, hearing, all at once.
Exactly. Neuromorphic chips are designed to handle multiple operations in parallel, simultaneously. This means much faster processing for complex tasks compared to the more sort of step-by-step processing in conventional computers.
So instead of a single file line, it's more like a multi-lane highway for information.
That's a great way to put it. Yeah, a super highway of information flow, this ability to handle so much at once, just like our brains do. That's really core to the whole approach. So
Okay, that makes sense. That parallel processing.
absolutely. And here's something that gets really interesting, especially for you out there listening. On-chip learning.
On-chip learning, what does that mean?
Well, many of these neuromorphic systems, they're actually designed to learn and adapt to new patterns locally right there on the computer.
Device itself without constantly calling home to the cloud.
Exactly. They don't necessarily need that constant connection for updates or retraining. Imagine maybe a smart thermostat that figures out your temperature preferences over time without sending your data back and forth all the time. That's the kind of local adaptation we're talking about.
Wow. So the real game changer here potentially is AI that learns your specific needs, maybe your habits, without broadcasting that data constantly.
That's it. It's a pretty fundamental shift, in how we think about AI and privacy. Huge implications for speed, efficiency, and data security.
Okay.
Oh, there is one more key feature, fault tolerance.
Fault tolerance, meaning they don't break easily.
Well, sort of think about our brains again. They can often keep working even if some neurons get damaged, right?
Yeah, the brain can often rewire itself and adapt.
Exactly. Neuromorphic chips are designed with a similar kind of resilience built in. If some parts or components fail, the system can often adapt and just keep operating.
Huh. So it's not like one tiny failure brings the whole thing down. Sounds pretty robust and resilient, especially for critical applications.
Yeah, very robust.
Okay, so we've got event-driven, low-power parallel processing on-chip learning and fault tolerance. How does this whole neuromorphic approach really fundamentally differ from the traditional AI that, most of us interact with daily?
That's a really good question. Think of traditional AI as often being very cloud heavy.
Right, needing powerful servers somewhere else.
Exactly. It usually demands significant power and often processes information more sequentially, step by step. You feed it data, it chews on it, gives you an output.
Yes, like asking a chatbot a question. It goes off to the server, comes back with an answer.
Perfect example. Contrast that with neuromorphic AI. It's designed from the ground up to be edge compatible, like a small, low latency edge computer.
Meaning it works well on the device itself.
Exactly, on your phone, in your car, on a sensor. Its processing is inherently parallel, mimicking the
Brain, like we talked about.
and as we discussed, it's incredibly power efficient. It's just a fundamentally different way of doing computation.
So it's less like calling a supercomputer and more like giving the device its own mini brain.
That's a great analogy. A mini brain capable of making smart decisions instantly, efficiently, right where it's needed. And that's the core disruptive potential for you, the user.
Okay, I'm starting to see the picture. So where are we actually seeing this type of brain-inspired computing start to pop up? Are there real-world applications that might affect you or me?
Yeah, we're definitely beginning to see some very promising applications emerge. Take autonomous vehicles, for instance.
Okay, self-driving cars.
Right. Neuromorphic chips could enable things like real-time object detection, identifying pedestrians, other cars, hazards, but with significantly lower power consumption compared to the systems used now.
Which means potentially longer range for electric vehicles, maybe.
Exactly. That's a real potential benefit for many people. Imagine your car instantly spotting a hazard without draining its battery nearly as much, or having to depend on information from servers in the cloud.
That does sound like a big step forward, especially for efficiency. What other areas?
Well, smart cameras are another one.
Security cameras, things like that.
Yeah, or even cameras and phones. Think about faster facial recognition, again, with less power needed. It could lead to more efficient, more secure systems for, communities or businesses.
Like how our own brains recognize faces so quickly.
Kind of mimics that efficiency. Yeah.
Okay, what about things that might directly help individuals more personally?
Well, consider prosthetics. This is a really exciting area.
Artificial limbs.
Right. Neuromorphic tech could lead to adaptive devices that learn the user's specific movements and intentions,
Oh, wow.
responding in real time, offering much more intuitive, natural control that could be truly life-changing for people using those devices.
That really highlights the potential.
Definitely. And then in things like drones and robotics generally, we could see much more autonomy, better situational awareness, letting them navigate tricky environments more effectively for all sorts.
For tasks like deliveries or maybe search and rescue.
Exactly. Things that could definitely benefit you indirectly, even if you're not operating the drone yourself.